can either make it cold or hot, and so we just alternate.
I would like my Texas weather back right now.
What's it like in Austin right now?
9 degrees.
Hell yeah.
It's October.
Oh, October's like one of the hottest months.
That's insane.
Yeah, we right now it's 87. Okay, so it's we're sub 90. We're sub 90.
It's getting cold.
That makes a difference.
No, it does.
Yeah, so we're I love it. I'm like all about hot weather now.
The thing is, I realized that I hate the cold, and I cannot survive it. It's physical pain, but I can survive in pretty hot. I'd rather my room be overheating than just not.
It's all about where you
Yeah.
Your body does switch pretty quickly.
Yeah, my partner wherever we wish to live temperature-wise, it's very different.
Talk about it.
It's a 2 temperature problem. It's
That was my roommate in grad school was from Buffalo.
Yeah, that's where my dad's from.
Yeah, similar latitude.
And then I'd come home and I'm like, what is this? This is a hostile environment. I cannot live here.
Yes.
Minimize is the purple sign is the one that has the QR
Up
code.
there. Okay, cool. Yes, I will do
I
that.
confirm the keyboard and guitar.
Oh, good.
Excellent. He's got it. Okay, cool. And then Sarah and I are doing drinks and snacks. So,
Well,
yeah.
Sounds good.
Good. Okay.
This is a crazy amount of screens that are all showing the same thing. But I understand.
I appreciate this one, so you can see what is being given. Maybe I already turned back.
Yeah.
Why do you need this and that?
That's new too. They didn't have this until about a year ago. Along with the mics,
The ceiling thing?
the ceiling mics.
Yeah.
Yeah, exactly.
The mics are super fancy.
Yeah.
I'm like, damn.
It is a huge revamp. They had right before I came here, this room was closed for I think the whole spring before I got here.
Damn.
So the Columbia were being held somewhere else while they
Maybe
revamped.
start with Supernova. Supernova did produce the dust.
That is true.
That's a nice.
That's a good segue.
Okay. Well, maybe we'll wait one more second to let people straggle in.
How do I check this on?
You what? Yeah. So
Is
just
it turned on?
nope. So if you just hit this, green light means it's on.
Okay.
Just clip it, and then I usually just put it
Yeah.
on it or something. And then yeah.
Come on, what's your talent?
All right. I think we got enough folks to get started. Welcome to, I believe, session 13, last session of today. The topics are going to be dusty, but the science is anything but. It's going to be some really cool cutting edge talks. And so we're going to start off with Nadine, who's going to show us, I hope, some gorgeous stuff from the Starforge simulation. So go ahead, Nadine.
All right. Thank you, Adam. So yes, we're going to talk about a bunch of dust stuff, and it is dusty science, but in a positive way. So yeah, I just started my Hubble Fellowship at the IAS, and I'll tell you why you should care about dust. So let's see if this works. Awesome. So on the right here, or I guess left, you see a visualization of a star formation simulation, and to get a sense of scale, this is about 10 parsecs across. And then if we could zoom in on the microscales of this cloud, we would see individual dust grains that go anywhere from 0.1 to micron sized. And these dust grains are made roughly of carbonaceous and silicate material. And by mass, they constitute about 1% of the interstellar medium of this cloud. And what I want to convince you of by the end of this talk is that dust is super important if we care about understanding star formation and how star formation varies. So what does dust actually do? Well, it sets the parameters and conditions that allow star formation to proceed. So it dominates the opacity across these regions, so it affects how our photons are actually being transported. It governs the cooling and heating in these high-density regions. It also can absorb radiation to launch radiatively driven winds, affecting the dynamics around some of the stars. And lastly, it plays a very important role in the chemistry that goes on because it gives us the surfaces that act as catalysts for formation of molecules like molecular hydrogen. And all of these processes will now depend very sensitively on our dust models. So very basic parameters that we should care about is firstly, how much dust do we actually have that we could use for these processes, which we think about in terms of a dust to gas mass ratio, right? And then the second thing is, what is the size of these dust grains that we have? Is it mostly smaller grains? Is it mostly larger grains? And this tells us how much surface area do we actually have where for these processes to proceed on. And in star formation, we make two strong assumptions about these two parameters. So the first assumption that we make is that the dust to gas ratio is constant everywhere, right? So that's roughly that the gas is glued to the dust, or the dust is glued to the gas. The second assumption that we make is that the grain size distribution is the same like that we see in the diffuse interstellar medium. And what I think is that these assumptions are fine for other regions of the interstellar medium, but we simply can't really use them in star-forming regions, or at least we need to relax some of these assumptions. And the reason we need to relax these assumptions is this dust to gas ratio in star-forming regions is a function of your turbulence, your magnetic fields, your radiation field, and all of these are highly variable and will give you fluctuations in the dust to gas ratio. Second thing is your grain size distribution is a function of the temperature, density, and velocity of the gas you're in. And for conditions in giant molecular clouds, which are cool and dense, you actually expect to be more towards the larger grain population. So what I want to ask is, what happens if we relax these assumptions? What more can we learn about how star formation proceeds? So to do that, I use the StarForge simulations. This is a visualization that was made by Mike Grudich, a previous Hubble Fellow. And you're seeing a kinematic map of one of these simulations. So orange gas is highly turbulent gas. Purple gas is sort of calmer. And in these simulations, we're solving the magneto-hydrodynamic equations. We have live radiative transfer. There's heating, cooling, and chemistry to resolve the formation of individual stars. And once these stars form, as you can see, they then launch bipolar outflows. They also release radiation, as you see these H2 regions that are forming, and they have stellar winds. And if they're massive enough, they can go supernova. And what my simulations do is I extend this by now adding Lagrangian dust particles and tracing their dynamics throughout these clouds, and then coupling them self-consistently to the thermodynamics, to the radiative transfer, and the chemistry, and see, okay, how are these processes being affected by the changes that we see in the dust, and how do the changes that we see in the dust affect the star formation? So to jump right into some of the more interesting things that we see, so we see these dust evacuated regions around massive stars. So this is sort of an image of the dust to gas ratio, where at the center here is a 2 solar mass star that is formed in these simulations. And what you can see is that towards the center, there's about 10 times less dust than you would assume if you were assuming that the dust is glued to the gas, and that dust is sort of being pushed out further out from the star. And then you can ask, okay, but how does this actually affect the star itself? So one parameter that we thought of is the amount of dust that actually makes it to the star itself, right? So this is the ratio of accreted dust to accreted gas as a function of stellar mass, and then I can take this line, which is going to be the null hypothesis of a constant dust to gas ratio. So anything below it will be sort of dust poor, anything above it will be dust rich. And then if I put on the distribution of these stars that I see in a given simulation, so here this is the interquartile and interdecile ranges for the stellar population, you see this sharp drop off towards the high stellar mass end. And to study this, we could then turn on and off different sets of physics to see when this trend disappears. And we see that the dominant driver of this is radiation pressure on the grains, which sort of makes sense and is consistent with this picture where you have some infall that is dragging your dust along with it, but then you also have radiation from the internal stellar source that is pushing this away. And then there is some radius they will balance, and depending on your stellar mass, that depends how much dust actually makes it down to the star. Another interesting thing in this figure is this giant range in the amount of accreted dust to accreted gas. And this is much, much wider than we would expect from even a very conservative estimate of our statistics. So an obvious question is, do you actually see this in real life? So do observers see this? So if you look at spectroscopic studies, and especially now with Gaia, we could get very good measurements of open clusters and then look at their metallicities. And what people found, as shown here, this is sort of like the cumulative distribution of a given stellar cluster. And on the x-axis is how much metallicity variation do you see between stars. And you could also measure that in terms of a mass. So what people are seeing is about 10 to 30% of stars vary about 0.1 to 0.2 dex in their metallicity. And if you convert that to mass units and make some assumptions about how thick the surfaces of these stars are, then you get something that's very close to Earth masses. So people are like, aha, then it must be planets driving this metallicity difference, right? So you have a planet. This planet is going to crash onto your star and leave all this refractory rocky material on its surface, and that's why these sort of mass ranges arise. But what we also find in our simulations is, well, what really is a planet? A planet is just a really, really, really big dust grain, right? So what if it was just smaller dust grains, right? So what if instead of accreting this big dust grain in one go, I'm actually accreting a little bit of grains throughout the star's lifetime. So here I'm showing two of my clusters, so a small stellar cluster at high resolution and a larger cluster at a little bit lower resolution for a combined number of about 1,000 stars. And you see that this goes straight through the observational constraints. And we can infer the same pollution masses that people are seeing. And what I'm arguing isn't that planet pollution doesn't happen, but that you can actually have multiple pathways to generate the same exact observational signature. And lastly, I want to quickly talk about the grain size assumption. So ideally, you'd want to do this self-consistently, like actually tell what the grain size in these conditions would be. But it's highly uncertain and computationally expensive. So as a first look, what we did is we take our diffuse ISM model and then go 10 times larger and then 10 times larger, and then see what difference does that make to star formation. Does that even matter? So one way to parameterize this is by looking at the star formation efficiency. So here I'm showing just the total mass of all the stars that form at a given simulation as a function of dynamical time for these different grain size distribution. And as I vary the grain size about a factor of 100, you see an order of magnitude reduction in how efficient star formation could be. And for reference, one of the parameters that we usually think of when we think of varying star formation efficiency is metallicity. And this is much, much larger than the equivalent changes you would see from metallicity, which is usually a reduction of a factor of 2. And this could happen from any of these processes that I was telling you about earlier, but the dominant effect is if you have some photons that are propagating through very small dust grains, then this is very opaque. They can't really get through, so you keep your cold, dense gas, good for star formation. But as you go towards larger and larger grains, they can simply leak through, heat up your gas, and essentially quench star formation very quickly. So with that, I'll leave some of my takeaways and take any questions.
Time, so we've got some time.
Nadine, you mentioned the connection, the effect of grain size to star formation efficiency, and that is it's more important than metallicity, right? But essentially, grain size and metallicity are correlated, right? I'm not sure exactly if there is, we know exactly how, but there is some kind of correlation. Can you, if you put them all together, can you assess how how it might affect the star formation efficiency?
Yeah, so that's
both effects are incorporated into the model. That's what I'm saying.
Yeah, I guess I can't tell exactly how that would, how much that would change things a priori. But I think it's also important to note that that correlation only gets you so far. So at some point towards some grain sizes, the metallicity won't actually be varying, but you could still have much larger grains. So it's not necessarily always causation depending on the dynamic range that you care about. So as you go to these very, very massive grains, they're growing mostly because of coagulation, which is relatively independent of metallicity.
Yeah, Sarah.
When you're talking about the variations in grain size, are you assuming the same overall mass of dust is available? And so it's and that's what lets you, then you are more efficient when you're smaller grains.
Yeah. So it's motivated by this efficient coagulation model where you just stick the small grains together and get larger.
Actually have more space.
Yes. Yeah.
Quick question? Yeah.
My question is also about grain sizes. So what observations exist from giant molecular clouds? What do we know about the grain sizes? Because presumably the giant molecular clouds have been studied.
Yeah, so inferring grain sizes is very difficult and also very controversial. So it really depends who you ask and who they believe. There are some observations that tell you that you could have micron and above grain sizes in these conditions, and that's technically possible. But all of these are you need to make a lot of assumptions to get that out of the model. So they're very poorly constrained because they're very opaque, essentially. So it's very difficult to tell how large or what the spectrum really goes from.
Okay, let's thank Nadine again.
Can you all hear me okay? Yeah, I can barely hear myself. Wow, I don't think I've ever been teed up so well. I'm going to be talking about dust, its impact on high redshift star formation, and grain sizes. So fantastic. Cool.
All right, Jed is going to take us to much greater distances.
Yeah, thanks, folks. I'm really excited to talk to you about dust. A lot of what I do is kind of couched within the study of galaxies over cosmic time, recently mostly at very early cosmic times. But what I do as someone who loves dust is I try to take all the wisdom that, like we just heard in Nadine's talk and that we'll hear in later talks throughout this session, and try to convince high redshift galaxy astronomers that this is like the most important component of building their early galaxies. Because I'm a firm believer that dust is the secret sauce for galaxy evolution. First off, we know that most of star formation over the entire history of the universe occurs deeply embedded within clouds of dust. So if you just want a census of star formation over cosmic time, you have to look with instruments that are capable perhaps of peering through the dust or looking at dust directly. And that's what a cosmic star formation rate density plot like this one encapsulates, where the orange is dust obscured star formation. We're recently pushing out to much higher redshifts with instruments like JWST and ALMA as well, and it's sort of begging the question of when is the dawn of dust? When does dust become really important for controlling early star formation and kind of setting the seeds for galaxy evolution for the next, say, 13 billion years? It's been sort of like a historical wisdom that dust takes a really long time to grow and be produced, and so it's been commonly ignored in sort of early galaxy formation, but that picture is really starting to change. ALMA has directly detected dust in continuum emission at a redshift of 8.3. We see indirect evidence based on the ratio of H alpha to H beta possibly being greater than what's allowed by case B. In spectroscopy, this is a MIRI LRS spectrum, out to redshift 12.3. We see metals in galaxies out to a redshift of 14, right? So the universe is making galaxies very early, and it's assembling metals in those galaxies, which you take a bunch of them together and you have dust grains quite quickly. Okay, so how do we think about dust at these early cosmic times if it's so important? What I want to talk about is that if we have dust really early in the universe, we're sort of in this era of supernova dust. And what I mean by that is this is a figure from a recent review paper showing the dust to stellar mass ratio grown in a galaxy as a function of age. And in order to build an appreciable amount of dust in galaxies, here we're limited by cosmic time. AGB stars are going to be subdominant until about a gig a year. And so if we find dust in these galaxies, it has to come from supernova yields. Those are these blue trends that are growing dust in galaxies really quite rapidly. And the really interesting thing is that the dust that we think comes out of supernova, especially in very early cosmic times, is probably very different than the type of dust that you would get through your typical AGB channels. And the main thing that I want to highlight is that the dust grains that we think are, I'm saying formed in supernova, but to Wynn's talk earlier, it's really just like surviving the entire supernova and then injection into the ISM process. But the point is that those dust grains are weighted towards much larger grains, and we just heard it from Nadine about how that change in grain size is really, really important. These larger grains are preferentially absorbing in the optical. That's what this figure down on the right here. This is just the wavelength that a grain of size like A preferentially absorbs it. So as you move to larger and larger grains, you're losing UV extinction and you're picking up a lot of optical extinction. We just had a few questions about, how much can you change grain size distributions while preserving the total mass of the system? While small grains comprise most of the surface area, and they're very important for radiative shielding, everything basically below 10 to the minus, a few times 10 to the minus 2 is only about 1% of the total dust mass. And so you can produce the same amount of dust from these channels and have drastically different grain size distributions, but you're not making wildly different assumptions about the total dust yields needed to produce those scenarios. So, what that allows for is very subtle changes in grain size distributions. Okay, so as of, a year and a half ago, the state of the art for modeling galaxies at early cosmic times, if you thought there might be dust in them, what you would do is maybe assume a Milky Way-like law, but most likely assume an SMC attenuation law. And this was based on some observations that this type of attenuation might work in low metallicity galaxies. And hey, galaxies in the early universe, guess what? They have low metallicity, so cool. But I don't think this is really the correct picture. So here I'm showing some results from Deshikar Narayanan. He's written this code that was meant to predict the incidence of the 2175 angstrom bump, which you're seeing here. And he was able to predict it, and it occurs at about over redshifts of 6. That's kind of where we've actually observed it out to, redshift 6.7. But if you roll back the clock here and go to earlier cosmic times, this is the attenuation law you get. It's effectively completely gray. Super bizarre. What this means is that the attenuation sort of across the rest frame UV and into the optical is gray, and it's not going to leave much of an impression on your like observed spectrum at all. And so what we did is we went in and we said, if dust is very exotic, if it's really these large grains that are preferentially absorbing at the optical and you're losing all of that UV attenuation, what impact does that have on inferring properties of galaxies at early cosmic times? We found these are the chi-squareds that you get just to the rest frame UV. We found that we got better fits to the rest UV SEDs of galaxies from redshift 6 to 12 when you assume this very shallow supernova-driven dust. We found that you have larger inferred AVs, which allows for larger stellar masses. And also, we found that we could back out the fits to these galaxies with lower total UV luminosities. Okay, what does this all mean? It means that we're making the wrong assumptions probably in modeling some of the first galaxies, should dust be an important component of them. If that's true, then our stellar mass functions might be biased low. And finally, our ionizing photon production efficiencies might also be biased high if we're overestimating intrinsic UV luminosities. That's going to have implications on, cosmic ionization. And actually, we were able to, we think that maybe having some dust lowering the intrinsic UV luminosities of these galaxies would help with the too many photon budget crisis that JWST was kind of pitching. All right. Okay, so dust, really important not only for triggering star formation and kind of regulating it, but also in dictating the inference that we make on galaxies at early times. I'm going to pivot now and switch from this era of supernova dust to kind of the era of typical dust-obscured star formation, which occurred about like 10 billion years ago. This is cosmic noon. Redshifts of like 1 to 3. This is when 50% of all stars in the universe today formed in luminous infrared galaxies at this epoch, heavily obscured by dust. So dust is playing a really important role, sort of shielding these nascent cocoons of star formation. To probe directly into the dust conditions at this time, we ran the first extragalactic survey with the LRS instrument on JWST MIRI. And the goal was to target PAH lines in galaxies, ratios of which you can use to back out grain size distributions directly. And that's of polycyclic aromatic hydrocarbons, not necessarily the entire parent sample of dust, but PAHs are a really important component of that. Here I'm showing a gallery of the spectra that we have. We have 37 gorgeous spectra in spanning redshifts of about 0.7 up to 2 in galaxies that are completely dominated by star formation. And also we see strong power laws indicating, a rapidly growing AGN, supermassive black hole at the centers. This has been a wonderful team to work with, and I'm just highlighting some of our junior folks here who have put in a lot of effort on getting this data to where it is, and in such have kind of become experts on using this observing mode. And they're all like in the midst of graduate school or starting graduate school soon. So they have really exciting careers ahead of them with infrared spectroscopy. Here's another look at some of our data. We see polycyclic aromatic hydrocarbons at 6 and 3 microns. These are some of the main features that we are going at for the purpose of the science we described in the proposal. But we see all sorts of wild things. We see water ice absorption. We see CO2 and CO ices. We see narrow emission lines. In the AGN of the sample, we see 3.4 micron absorption. So that's dust and absorption. Again, this is at cosmic noon, so 10 billion years ago into the history of the universe. This observing mode, LRS, is just simply fantastic. And I got to meet with a lot of the MIRI team, today and over the past few days, and it's been super fun to geek out over this data with them. Here's another way of visualizing that. Here I've taken the spectra and stacked them. I've kind of like plotted them by wavelength and then ordered them by integrated flux. This was inspired by Joy Division's Unknown Pleasures record, which in turn was inspired by the 1970 PhD thesis that Harold Kraft put on of, I think these are pulsars. That's just cool. Okay, so what are we actually doing with this data? Well, I was talking about polycyclic aromatic hydrocarbons. Pause, depending on their size, and here I'm just representing the change that you get versus an ionized PA or a neutral PA. These are all the different emission bands that they light up in. You can see they're very different when you turn some of these knobs. And so what we did is we, using this new JBOST data, we were able to kind of take these feature ratios and get constraint on the neutrality fraction of dust grains at high redshift, as well as the typical sizes. And I'll just map these. So here I'm showing the 7 micron feature. Here I'm showing the 11 micron feature and the 3 micron feature, which we needed JWST to get at redshift 2. We didn't find much evolution relative to like local analogs along the typical charge of these grains, but we found a 3x increase in their typical sizes. This might have to do with like things like Nadine was talking about. High redshift galaxies are, have higher gas fractions. The gas is much more dense. They're exposed to stronger radiation fields. All of that might be shaping the coagulation of these grains and shifting them larger. But the really cool thing is then thinking about like, okay, what does this mean for star formation at the height of cosmic star formation, right? How are most stars forming? How is dust playing this kind of key role in sustaining star formation rates of hundreds to thousands of solar masses per year over, hundreds of million years? And with my kind of pet theory, this is the heating rate that PAs follow. This is part of an important photoelectric heating process that basically sets thermal balance in the ISM over 6 orders of magnitude in density. And what you see here is as a function of the size of a PAH, what its kind of heating fraction is, or what its heating rate is. And as you change this at the level that we think we're seeing differences towards high redshift galaxies, you get a 30%, in this case, decrease in the heating efficiency of gas. And I think this helps prevent ionizing photons from injecting energy into cold molecular gas, and that helps sustain really vigorous and prolonged star formation. I'll leave y'all with my takeaway thoughts and happy to take any questions. Thanks.
Perfect, very nice talk. Questions for Jed?
Hi, super cool stuff. I wanted to ask, connect both of these things. So you spoke about supernova dust and you spoke about PAHs. Mm-hmm. My sense is supernovae usually produce oxygen-rich dust.
Okay.
So where do you think this carbon-rich dust in these high-redshift galaxies could come?
It could be carbon that's seeded into the ISM just from like general star formation and metal enrichment. The survival fraction of carbon-rich dust versus oxygen-rich dust out of the things that we think are producing dust at very, very early cosmic times, I really have no idea. So I actually don't have a good answer for you, I'm sorry.
I have a very basic question. How do you get the size of the dust grain? You get the path?
Yeah. So this is super cool. So this is like the only part of my job where I can actually go look up like laboratory astrophysics papers. And so we rely on people who make polycyclic aromatic hydrocarbons in labs, and they calibrate these absorbance characteristics as a function of the charge and the size of grains. And there's been extensive work going back to like early 2000s Bruce Drain's models, and then like refining those methods, some using like more numerical methods, others really relying on laboratory techniques. And here I'm showing one of my preferred model grids from Merikudakis et al. 2020. But yeah, it's some combination of like lab astrophysics and like chemical modeling. Yeah.
Maybe one more quick question while Tavisha comes down.
Yeah. Can you tell us more? I forgot the acronym of this dust model that you put out, but can you tell us more what the assumptions going into that? Like, what is the compositions being assumed there? How are the grain set distributions being self-consistently found?
Totally. So, okay. I could point you to the papers where you could probably extract all the details that you want. The important things about those simulations that are predicting the very exotic dust attenuation laws is that they are doing dust on the fly in a cosmological zoom-in simulation that is tracking the radiation field for self-consistent updates on what the dust would respond to that. So composition, I don't know.
Okay.
Yeah, I don't know. Whatever standard theorists assume. Yeah.
It's related to the earlier question
Yeah.
about supernova being either like oxygen rich versus carbon rich.
For sure. I'll look into that. Yeah. Thanks.
I think we are out of time, but find Jed at the end of the session.
What? How much will the t-shirts cost? The t-shirt. How much are the t-shirts going to be? Your spectrum.
Oh my gosh. Fantastic idea. $50.
Okay, I guess you're next.
Yeah.
Nisha has to plug in. I didn't either, but that's fine. Great. Is that the that's top button? Okay, good. All right. All right, next talk will be Andrew telling us about DIBS. Take it away.
Thanks. So my name is Andrew Stadry. I'm a second-year Hubble Fellow at Princeton. And my research program really focuses on trying to understand dust in the interstellar medium. And today I'm really excited to share with you some of our recent work in which I think we've finally realized diffuse interstellar bands as a unique new chemical tracer and handle on the variation in the interstellar medium. Okay, so the phenomenology of dust extinction is pretty well known at this point and is beautifully captured in this image. There's some stars that get fainter as they go behind the dust and redder before they finally lost behind the dust filament. So we call that, in an absolute sense, the extinction, the comparison of the observed magnitude versus what we would have expected to see without the dust in front of the star. And then we also measure this relatively in terms of color changes, the change in the observed versus the intrinsic color, which we call reddening. That's just easier to calibrate. And so you can understand the name reddening by just looking at one of these extinction curves, very similar to what Jeb was showing before, where you're plotting the extinction at a given wavelength versus some reference wavelength. And you can see that it peaks in the blue, which is why we see the light looking redder as it passes through the dust. Okay, and so in general, people have for a long time made the assumption that the variations in this extinction curve can be described very well by a single parameter model. And that parameter is RV, which is basically 1 over the optical slope. And so here I'm showing you one of the more famous models, CCM89, and the variation of the extinction curve with this parameter RV. And the physical interpretation that is conventionally held for this is that as RV increases in grain models, this is connected to an increase in the grain size, the average grain size in the population, causing the slope to go down. Now I say conventional because there's been recent evidence that has shown the variation in the PAH population may have a larger role in changing this RV variation than was previously thought. And even within the dust models themselves, if you tune, for example, the carbon to silicon ratio, you can drive RV variation. So there can be chemical variations that could drive this in addition. Okay, but if you believe and you stay within the single parameter extinction curve model, you might want to ask, how important is this really to me? And you live here, and this is 2.5 kiloparsecs out in a top-down view, and the answer is it matters quite a lot. RV is varying between 2.3 and 3.9 in the solar neighborhood. So you have to care. And even if you don't care about single parameter models and you were just like trying to make these approximations, it's important to understand that these extinction curves have many more features. It's not just a single parameter family. Recently, there's been some really nice work by Gordon, Fitzpatrick, and Massa over the last few years showing that if you assume a really, really smooth extinction curve, you see the data actually demands that you have these few little bumps here that might be a little hard to see. They then call intermediate scale structure. These are like really broad features in the extinction curve. And even on even smaller scales, we know that there are diffuse interstellar bands. So here's just an example of a solar spectrum or stellar spectrum observed by apogee if there is nothing between us and the star. But small molecules associated with this dust have absorption features, one of which I'm showing here in red, that are much narrower than the intermediate scale structure I just told you about, but a little bit broader than these stellar lines. So we have this really large diversity of features that are changing across different wavelength scales on the extinction curve and a varying extinction curve as a function of space. And so I was really motivated in my research program over the last several years to answer this question, which is whether or not we can actually detect and measure chemical composition variations that might be present and accompanying RV variation that we see spatially. And the answer is we didn't really have the data sets to respond to this question. And so myself and my collaborator on this work, Greg Green, worked at this problem from different ends to build the data sets to answer this question, and I'll do that for you today. So here's just a summary of the different features on the dust extinction curve. Their width is on the y-axis, their center wavelength is on the x-axis. I worked from the bottom up to build us really nice catalogs of diffuse interstellar bands. So this is the 8623 Amsterdam DIB and Gaia RBS, and one in apogee that I'll be focusing on a lot today. And from the other end, Greg worked to build catalogs of RV and the intermediate scale structure features from Gaia XP spectra. So the way that he did that is doing a forward model from stellar parameters to try to predict what the spectra and Gaia XP should look like, and doing this in the framework of a single parameter family of extinction curves. But to go beyond that, what he did is then just compare the observed spectra to the predicted spectra, look at that variation, and using a covariance-aware PCA method, decompose that into different components of extinction variation. So when you do that, the first thing you get is an average extinction curve. Okay, and this looks like every extinction curve you've seen so far today, not all that exciting. And the coefficient in front of that basis vector is just going to be extinction. So I'm showing you the average value of those coefficients plotted on the plane of the sky here. But if you look at the first most important variation in the extinction curve as a component, this is what the basis vector looks like, and it's mostly driving changes in the optical slope. So you might think that the coefficient in front of that basis vector is related to RV, and in fact it is. It's basically linearly proportional to RV over most of parameter space, and so this plot on the right is basically showing you an average RV map on the plane of the sky. So I won't belabor this, but there are many other parts of this variation that are important, and these higher order basis vectors clearly emphasize these two intermediate scale structure features that I told you about before. I'm showing you these dashed gray lines that are strongly peaked in these basis vectors. And so these higher order coefficients x sub I are really parameterizing variation in those intermediate scale structure features. Now, when you choose a basis, there's one key choice to make, which is the sign. There's an arbitrary sign on these basis vectors, and I've chosen the sign such that these intermediate scale structure features all point up. So that is, as xi increases, the intermediate scale structure features are getting stronger, and we'll need that for interpretation in a minute. Okay, from the other end, building up a catalog of these narrow features, the diffuse interstellar bands, I applied a technique called MAGICS that I developed during grad school, which stands for Marginalized Analytic Data Space Gaussian Inference for Component Separation. And the basic idea is that you model your observed spectrum as a set of linear components that you have some prior on in a data-driven fashion. We did this to apogee. So we first modeled the spectrum as having some contribution from sky continuum and sky lines, stellar continuum and stellar lines. These data-driven models are a bit easier for everything but stellar lines, in which we have to build a hybrid model using theoretical stellar spectra from Core, which is a code written by Adam Wheeler at Flatiron that I also contribute to, and then doing data-driven corrections to those models. We also then model an ISM absorption feature, the diffuse interstellar band we're interested in, and then the residuals that should account for detector noise and unknown unknowns. So you might be a little bit scared when I say Bayesian model and priors, that like we might be missing what we're actually interested in if they're not consistent with these. But this model actually requires that all of these components sum exactly to the data. So you're just partitioning the flux that you receive from the universe into bins that are consistent with your knowledge, and anything that's inconsistent with that will just go into the residuals. And so you'll never miss any features. And when I also say the word Bayesian and posterior, people often get scared that this is going to be expensive. But it's actually quite fast. It runs in about 7 seconds per star, and we've run it over all of apogee DR17, which is 2.6 million visit spectra. Okay, so the standard way to look for diffuse interstellar bands is to assume a linear response model. That is, just ask in my residuals what portion of those residuals correlates with extinction, and just plot that as a function of wavelength. You see these beautiful bumps and wiggles, and these are the 7 strongest diffuse interstellar bands in apogee that we'll be talking about today. Okay, and if you care about one of them in particular and you want to model that line and make a catalog of its 0th, 1st, and 2nd moment of its line profile, you can do that. And we've done that. We've created the largest precision DIB catalog that I know of to date. It has about 150,000 detections of the strongest DIB in apogee. And here's an average on the plane of the sky and in a top-down view of the equivalent width of that diffuse interstellar band. And we expect this to get about 5 times bigger in terms of catalog size by the end of SDSS 5. Okay, so with these in hand, we can start to answer this question, but I actually want to answer a simpler question first, because the first one was kind of big. So we can ask, if we believe the answer to this question is yes, that there's chemical composition variation with RV variation, we would then expect variation in RV measured by dust, these broadband extinction variations, to drive variations in the ratio of the strength of the dib to extinction. So we can just test that question empirically first. That is a very conventional plot that's made in the diffuse interstellar band literature. So you plot the strength of the dib on the y-axis, the H-band extinction on the x-axis, you draw a line. And every time I look at this plot, I ask how much of this scatter is real? Like how much of that is scatter in excess of measurement uncertainty? And to answer that question is why I spent years developing a Bayesian model to get robust uncertainties. The answer is a lot of it is. A lot of it is real. And if you include variations in RV and these beyond RV parameters in your model, you get a much tighter relationship in your ability to predict equivalent width. And you might ask, who cares, Andrew? You're talking about tiny little bumps on the extinction curve. I don't even care about extinction to begin with. Hopefully that's not you, but maybe it is. But this is actually a big effect. This is a 20% change in your predicted equivalent width. Right? This is not like a negligible sub-few percent effect. Okay. Just to be very explicit about what this new model is, everyone for the last several decades has been modeling the equivalent width as being directly proportional to extinction, and we're just adding on these additional terms for RV and beyond RV variation. And the important thing I want you to take away here is to look at the sign of this slope, the sign of this coefficient. For the 15273 angstrom dib, all of these slopes are positive. And so based on the sign choice that I emphasized before, this is telling us that in every direction of dust variation that we see, the dib is getting stronger while the intermediate scale structure features are getting stronger. And that didn't need to be true, right? Like this is a fundamental statement about correlations that we're making between small scale and intermediate scale features on the dust extinction curve. So now, just in case you didn't think this model was useful, we can plot the residuals on the plane of the sky using the prior model that's just dependent on extinction. You see these large spatially correlated residuals. And if you extend the model to the model that I'm proposing here, we significantly reduce those residuals on the plane of the sky, although there's still some structure to explain and understand. So everything I've been showing you here is using an integrated measure, the equivalent width. But there's no need to integrate, right? We can do this linear response model per wavelength bin and ask what basically the spectral response of the residuals are to RV variation and these other coefficients. And so if we look at just the first term in that model, that's the standard one I've showed you before that people use to measure diffuse interstellar bands. Here are the two strongest ones in apogee. But the first one, the response function with respect to RV is quite interesting. You see there are these pretty significant line shape changes. There are these double peak structures with this asymmetry in the peaks that we observe. And we'll come back to trying to understand what that is. And then the higher order ones look very much like just rescaled versions of the extinction profile. And so that is to say, if you're slightly more careful and you look at all the rows for an individual dib column, you basically find two principal components of variation in these spectral response functions. Let me zoom out to a few more dibs to emphasize the fact that we actually see the dibs separating in terms of their response signatures to variation on these different directions on the plane of the sky or in this dust space. So the white boxes are showing you places where the dibs aren't really responding, and the pink are showing you places where the dibs are getting stronger with respect to variation along that coefficient. And you can see they separate out into these sort of patterns and families. What those families are telling you are that these different signature dibs have different chemistries or different ionizations, which is causing them to separate as the ISM is varying. So this is just a final zoom out picture of the sort of complicated thing I've been showing you pieces of, showing you what I think is clear evidence of chemical composition variation along with dust curve, broadband dust curve variation. The one feature I haven't emphasized yet is the 15616 angstrom dib. And just in case you haven't believed the rest of my story, this dib has the sort of anomalous property. It's the one of the 9 dibs that we've studied that points the other way. So as RV increases, this dib gets weaker. All the other dibs are getting stronger. So this is a clear evidence that we're changing the relative prevalence of certain molecules as we vary along a notion of directional change in the ISM. Okay, so I just want to end by showing you one slide on ongoing work. This is work that's joint between myself and Christian, who's a really excellent graduate student, also in his final year at Princeton. And the idea here is to try to understand what this line shape variation that we saw in the RV derivative or the RV response function is actually coming from. And the simple answer is that we're able to model this as rotational substructure in this transition. So we're basically saying the molecule is spinning and its rotational transitions, and understanding this profile as both a combination of the direct and the temperature derivative are able to explain both the double peak and the asymmetry in the double peak that we see with just a few parameter models, sort of 7 or 8 parameters. We can then put a posterior on those parameters, for example, the rotational temperature, and most importantly, the moments of inertia of that molecule, and that allows us to translate this directly into constraints on the geometry for the molecular carriers of the diffuse interstellar band. So this is not a direct constraint on telling you exactly what molecule it is, but it's narrowing down the chemical space that we have to investigate, and we can do that in combination with our friends in the radio and laboratory sciences. So with that, I'll just put up my summary slide, and I'm more than happy to take any questions. Thanks.
We have, time for maybe one question. Yeah.
So I deal with dust as a annoying component that blocks all the gas measurements. So my question is slightly about the larger wavelength. What is the total wavelength range which you're seeing this variation?
Yeah, so I showed you things that are basically from the optical to the near infrared. So sort of from 400-ish nanometers, 380 nanometers, all the way to 1.5 microns. That's where I'm characterizing the extinction curve and its variation here.
Do you expect it to contribute to larger wavelengths?
That's a good question. I think we're still trying to understand the extinction curve in the far infrared and the mid infrared, and what that looks like, and where the transition to emission turns on, and what features you expect there. And I think we'll find more things with upcoming high resolution spectroscopy and things like that. But I think you do expect there to be variation. You expect the grain properties to be varying. You expect the grain chemistry. I mean, this is clear evidence that the chemistry of the ISM is changing. You expect grain size variations. So I think you do expect it, and the question is to what magnitude. And here, at least, I'm showing you that we now have actual observational evidence of the chemical change accompanying the RV variation that people have studied for years. And so I think you have to worry about it. Yeah.
Can I ask one?
I'm going to start getting Tavisha set up, but yeah.
Yeah, so you showed a top-down view of within 10-ish kiloparsec or something.
There's 2.5, yeah.
Yeah, roughly, yes. I mean, visually it looks like there are different angular scales. Some of them are very small angular structures and some very large.
Yes.
How do you expect it to vary with wavelengths?
I expect you to have similar variations. Those are mostly driven physically. Those are driven by different star forming regions, different OB star associations. So I expect that those property variations will be similar in those angular scales. Some of the reason for what you might have been seeing is that our resolution on the map falls off the further and further we go away from us. So I don't think that should change too significantly with wavelength. Yeah. Okay, thanks.
Let's thank Andrew again.
Thank you.
Okay, and last but certainly not least for the session, we have Tavisha, who's going to be talking about dust in the best galaxy in the universe, M33.
So if you notice my title, it's quite different to what I promised in my session / abstract. But I do promise there will be an M33 map, but I realized that this is my last symposium, and I really want to give a broad overview of what I've been doing in the last 2 years, and what I'm sort of excited to be working on in the next few years as well. So I was very much a dust person. I loved it. I still love it. I think it's amazing. But what I will sort of add is, if you start looking at the baryon life cycle, which is the stars, the gas, and the dust and the gas is sort of embedded in this whole cycle. So the gas is also there. So I've sort of started becoming one of those people who've sort of dabbling in the gas as well now, and trying to sort of bring all of these components together to try and sort of tell a more complete picture in sort of some of the research that I'm doing. And this came up in quite a few of the talks, I think, but I'll sort of summarize it here. Another reason why I started sort of putting all of these components together is because of what we call the baryon memory. And so what this sort of means is that the stars they get perturbed sort of in a more long-term scenario, whereas with mergers and that sort of thing, so they carry these sort of many giga-year memory in them. Whereas the dust has sort of this intermediate scale memory, like they have the memory of the supernovae, they have sort of these grain scattering effects that have their grain formation that's happening. So it's kind of this intermediate phase in memory. Whereas then the gas is sort of right at the end of that, where they have this mega year memory with turbulence, with star formation, things getting blown up. It's sort of quickly changing, so it forgets very quickly. So for us to be able to understand, say, our Milky Way or like nearby galaxies, which is what I'm interested in, you kind of have to bring all of these pictures together to sort of explain a coherent picture of what's happening. So I'm going to sort of talk about 5 of the projects that I'm like super excited about that I've been working on. And one of this is I'm going to go basically in scale. So I'm going to talk about the smaller scale first, and then sort of expand out to the larger galactic scales. So this is a project that was led by my CUNY master's grad student, who's great. So the idea for this project was we looked at the Betelgeuse's circumstellar dust emission in ALMA data. And what we wanted to see is what does the circumstellar emission look like, and can we model dust masses, so in grams per centimeter cubed rather than in grams per centimeter squared. So get a 3D dust mass estimate, which can then later be fed into supernovae models. So that's totally not my area, but the idea is we produce sort of a preliminary data set that can be used in supernovae modeling later. And what Iman did was she took the ALMA very high resolution and this very low resolution data set from Anita Richards and Pierre Carvella. And we subtracted the star out. And already just in the low resolution data set, you can see this emission. And what we did was we subtracted the star out, and then we started seeing a lot of this extra structure, especially some of these sort of brightening effects that we're seeing. And we're sort of seeing this bipolar effect in the ALMA data. And what she did was, it was sort of very simple transformation. She took, so there was some assumptions I went into this, like spherical symmetry had to be assumed to do inverse Abel transformation in general. But then she did Abel transformation, and now we're sort of, we have this dust mass estimates in grams per centimeter cubed now. And what we can see is this structure here. So we sort of have this decrease in dust density, and then suddenly there's a peak here, and that is sort of all of this extra dust that we're seeing in the circumstellar envelope. Yeah, and then from sort of the small star scales, I talked a little bit about EOS in the last symposium. I introduced it, and EOS has been this incredible little cloud that we've been studying. It was first detected in UV fluorescing hydrogen, in molecular hydrogen. So everything you're seeing here is direct molecular hydrogen. And EOS was one of these really like clouds that stood out. And what made EOS so special is also the fact that it was 99% CO dark. So you're seeing direct CO dark gas in molecular hydrogen, sort of. And it was the first time it was detected in fluorescing molecular hydrogen. And with sort of the 3D dust mapping that I've been doing over the last few years, what we were able to do is place exactly the size and the distances to EOS. And with that, we know that EOS is roughly about 94 parsecs away. And if we sort of, this is 2 scale and size, if we map it out and we can see it, it's a humongous cloud that we really should have been able to observe, but we just didn't look at the right data set to see it, and we just can't see it in our with our naked eyes. And over the last over the last year or so, we've really been able to characterize EOS, especially with these 3D dust mapping techniques. One of the cool things we found out was that EOS is sort of straddling the local bubble. It's like right at the edge of it. And what this lets us sort of understand is that maybe the reason EOS is sort of, I'm going to move over here because that's really bright. The reason that EOS is fluorescing and why we're seeing all this molecular hydrogen is because of the local bubble expansion. But then we went and looked at the gas velocity and broke that down with kinetic tomography to distance. And what that's showing us is that it's sort of expanding out, it's dissipating. But that doesn't sort of fit with this, it's purely just the local bubble that's fluorescing this cloud. But then when we looked at the 3D structure, what we realized is there's also this coseno B association that's in a direct line of sight underneath where EOS is. So what we think is happening is that some of the emission from the SCO-SEN association is sort of directly contributing to EOS being fluorescing. So it's sort of this combined effect of both being at the edge of the local bubble, but also being so sort of along this direct line of sight to SCO-SEN. And so we've been looking at EOS quite a lot, but then what about the rest of this FIM sphere data that we actually use to identify EOS? There's all of this extra structure that we're seeing in molecular hydrogen. And there's so much and one of the key things to know about all of this structure is that these are all very nearby structure. You can't see fluorescing hydrogen is very extinction dependent, and by about 2 AVs in magnitude, they drop out. You don't see anything. So what this means is everything that we're seeing here is very nearby. These are solar neighborhood structures. And it's also sort of very curious because a lot of these structures are on edges of bubbles. So we don't have a very clear conclusion of what's going on, but we think the bubble expansion or sort of some of this emission has something to do with the fact that we're seeing the fluorescing hydrogen. And there's all of these really nice structures. So this is another EOS-like structure that we're calling Cloud 2. Cloud 2 is actually 100% CO dark. You don't see it either in the Planck data or the CO DAME data. And we also have the LMC and SMC in it. So that's really cool. So we now have this LMC and SMC hydrogen, the molecular hydrogen mass for the LMC and SMC. And it's quite different when we compare it to sort of the CO gas that's being tracked with the LMC and SMC. This is very low resolution though, so there is some caveats to be taken into account when we're doing this analysis. But yeah, so this is something that's ongoing work that we're really excited about. And yeah, so stay tuned for that part. And finally getting to the dust map of M33, we've sort of gone through stars to molecular clouds to getting into the extragalactic scales. And so to develop sort of these dust maps of M33, what we did was we took the FATO data set, which was PI'd by Julian Del Canton, and we used the method that she does. So with the CMD that we can make, we can really nicely see the red giant branch and the red clump. And the idea is that it also tracks with the reddening vector. So we have this extinction model that basically tells us that there should be reddened stars in the back. There's a galaxy, a face-on galaxy with a single thick disk that you can then assume is extincting all of this dust. And then you have the foreground blue stars. So what we do is we remove the foreground blue stars entirely. We consider them contaminants, they're removed. And then what we end up being left with is essentially just the red clump. And what we assume is all of these stars here are reddened. And they're reddened because of this dust green. So this then lets us sort of build this Gaussian mixture model of reddened stars, unreddened stars, and contaminants. So here we have some of the examples. We have reddened stars, the unreddened stars, and this little one that's contaminated here. And it lets us sort of build these very high resolution dust extinction maps. So the M33 map that we made, it has about 250,000 total pixels, and it goes down to 10 parsecs, which is about 2.5 arcseconds. And we apply a Gaussian process prior to sort of ensure that the spatial smoothness is preserved. And we can really sort of pick out all these really sharp dust lanes because of that. So yeah, so this is the map that I was talking about. And you can see all of these little structures everywhere. We're recovering all the molecular cloud structures, but also these really sharp dust lanes that we're seeing now. And we can achieve this because of these sort of these high resolution maps. Now, another really cool thing with this technique is that we can also get some inclination information, because essentially your reddening is dependent on the line of sight. So if you have sort of more reddening, or this reddening fraction parameter that we call, it sort of tells you, is it more reddened or less reddened? And that will tell you, is it more inclined or less inclined? So here what we have is with 33, what we're sort of seeing is that this side of the galaxy is essentially less reddened, which means it's inclined closer to us, so it's sort of on this side to us. And then this side of the galaxy is much further away from us, so it's sort of inclined like that. So that's the type of picture that we're seeing with M33. And of course it does, so M33 has a warp, but what this part of it that we're looking at is sort of the inner region of M33 actually. So we don't have the full outer region. So we don't think the warp is affecting this part of it. So we really are just seeing the disk effects and the disk inclination effects. And so I've talked a lot about sort of molecular clouds and structure, but what about all the gaps? What about all the voids and the bubbles that we see in all of these star formation regions, that we see in all of these dust maps and gas maps as well, actually? So this is some, I'm really excited about this work. So this work is led by a third-year undergrad student at University of Sydney, Olivia Silcock. And what Olivia's been doing is she's been developing this code called BOBA. And what it does is it identifies galactic structure. So it identifies the underdensity, so all the bubbles, the cavities, and voids. And it can be done in both 2D and 3D, in simulations, and in observational data. So now we sort of have this way of consistently mapping from simulation bubbles and how they grow to sort of to the large scale structure to compare it to the galaxies like FANGs, and we can statistically start comparing them. And what Olivia is seeing is that when you take the true bubble sizes, the structures, because normally we draw spheres and ellipses essentially. But what we're seeing is they are nowhere near spheres and they're nowhere near sort of circles. They're very different, and there's sort of all these axisymmetric effects that are happening in this bubble structure. And so one of our goals is to compare this to the FANGs data, so we're really excited for that, and Olivia's working on that now. Yeah, and the last bit, so with my last slide, what I'm talking about is something I've been very excited about is sort of, so I've been working a lot on building these 3D dust maps, but like Andrew showed, we're sort of coming into this era where we now have the gas data. We have absorption information that'll let us really start mapping the kinematics in 3D as well. So for example, here we have the Galar potassium data set, and this is simply the velocity along the line of sight. And if you're familiar with an H1 curve, you can see that this data broken down by distance adds up exactly to the H1 curve very nicely. So you're seeing the radial velocities varying with distance, and this goes out to 5,000 kiloparsec. Parsec, sorry, 5,000 parsecs. So we're already, we're able to now start building these maps that'll let us break down both the distance information, so the position, and bring in this velocity information. And we're sort of coming to this humongous data era, because I think we've left the big data era a long time ago, and we're essentially in this humongous data era with missions like Roman and Rubin coming online. So we can really start mapping the Milky Way out in essentially the whole Milky Way really in both dust and gas to get the structure information as well as how it moves in the ISM, and really be able to compare it to all this amazing work that the Gaia team's doing and with all the Gaia data with the stars. So yeah, so I'll leave you all with that, and just say thank you to all my fellow fellows and all the leads. I've had an amazing time being a Hubble Fellow, and yeah, thank you.
Wow, that map of M33 is something.
I did promise it, so yeah.
Yes, no, and it was worth the wait. Maybe time for a couple quick questions for Tanisha. Go ahead, Abby.
Yeah, that map's amazing. I was wondering how it compared to far infrared millimeter emission based.
So I've been, I haven't done a complete ratio map of it, but I've been sort of comparing it to some of Chris Clark's work, and they look very similar, but we actually do pick out some of the structure that he's unable to fix, especially in the middle. So yeah.
Very cool.
Yeah.
I really like the Beatles' work. I know it was all the way back at the start, but do you have a sense of how much of that material within 1 or 2 R stars is actually unbound, actually passes, or is it just kind of like coming in, going out the main field?
I generally don't know that. That is something I'd be really interested to talk to you. I mean, how do you get that out? Because if that is something we can get out of the ALMA data, that is yeah. Or if any other data set can give that would be really cool. Yeah.
Yeah, go ahead. I mean,
Not about the
it's the end of this.
I had a question about the potassium kinematic curve. You said it lines up really well with H1. But in H1, we also know the cold and warm medium stuff, and I will ideally expect this to match up with the cold.
Yeah.
So how do you separate the cold and warm?
We don't at this stage. We're really just matching up what the potassium looks like to the H1 data, and we see that it matches up quite nicely, but it's not perfect. No, I agree. Yeah.
Yeah, so I would ideally expect potassium to include the warm. So
Yeah.
there will be some discussion.
Okay, so maybe if we sort of cut it out or something with, yeah, definitely.
All right, I think we're gonna have to call it there. Find Tavisha if you have more questions, but let's thank her again. That was a great talk. And let's thank all the speakers from this session. Great session. All right, just one announcement before we head out for the day. As you can see, I brought up the open mic slide here. Please sign up if you haven't. It's a lot of fun. It's going to be a lot of fun. It has been in previous years, and really anything you're interested in talking about or performing or whatever. Like we had lots of different stuff last year, songs and dance and sourdough. Arena talked about sourdough last year, and it's great, right? And so yeah, I think we lost Andy's contribution, so sign up. You went. Oh, okay. From 7:30 to 8:30. Okay, so you got to be building by 8:30
together,
or the door will be locked.
And you have to wear your badge.
And you have to wear the badge. Okay, great. That's good to know.
There are shuttles too. You have to wear.
I don't know when the shuttles are.
Yeah, I think sorry.
Okay, I think the shuttle information's probably on the slide.
Yeah.
Yeah. Okay. Cool.
Yeah,
Thanks, guys. See you later.
Please go.